Recording in progress.
Recording in progress. Let me quickly see whether here. Oh, got it. Okay, the audio is on. And we go back here. Good. Okay, so where did we leave off? Last time we were talking about identity-based encryption, and namely this notion of full security, where the adversary, gets in the first phase this oracle, right, which generates him identity secret keys. In the second phase, he can get identity secret keys for all identities except the challenge identity. And the rest is sort of as usual, right? In the first phase, the adversary picks a challenge identity and two challenge messages. The experiment flips a bit, encrypts MB under identity it star, gives the ciphertext to the adversary, and the adversary has to guess the bit B. And if he guesses it with probability noticeably better than 1/2 or non-negligibly better than 1/2, then he wins. Good. And now we have this notion of IB chem. Did I introduce the syntax for that? It looks like the syntax is good. So here now in IB chem, right? We always, let's take a different color. Let's take this color. So I did very efficiently put the same notion into the other notion into the same slide. So setup and keygen are the same for IB chem, or identity-based key encapsulation mechanism. But now encryption doesn't take message M, right? Let's leave that off. Alternatively, just takes MPK and it and outputs a ciphertext C and a symmetric key K, right? You can think of this IB chem as choosing a random key for you and encrypting this key, right? You're getting a ciphertext that encrypts a random key. And how would we use this random key that's produced by this enc? And now we call enc the encapsulation algorithm. How would we use this key? Well, just with hybrid encryption, right? You take your favorite symmetric key encryption scheme, AES, and use this key, this encapsulated key K, to encrypt the message payload you want to encrypt, right? This is how we use key encapsulation mechanisms, or chems. When I taught the crypto lecture, I typically discussed key encapsulation mechanisms, but I don't know if this is still the case. And the decapsulation algorithm, right, takes now an identity secret key and this ciphertext or encapsulation C and returns the symmetric key K, right? It's sort of like a two-message key exchange somehow. Now it's only identity-based, right? Good. Any questions? So, and the security for IB chems is now, well, slightly different. The adversary now just outputs this challenge identity. We don't need challenge messages, right? Because the message we're encrypting is sort of a random key. And good. And of course, we also abort if the adversary has queried his his key generation oracle on this challenge identity it star that he chose. Now we compute an encapsulation C star together with a key K, but the experiment just takes the key K and throws it off. Don't need it anymore. It flips a random bit. Oh, sorry. No. We do need the key K. What am I saying? We do need the key K here. Good. All right. If it flips a bit, if the bit B is 0, we keep this key K. We set K star equals K. Otherwise, we throw this K away and choose K star uniformly at random, right? So the challenge bit now just determines whether we keep the key that the encapsulation algorithm gave us, or if we choose a fresh one. Right, and now we give the adversary again a key generation oracle, which generates for keys except for the challenge identity its star, and we also give him this key K star and the encapsulation C star, right? And now he needs to guess whether this K star is actually the key that's encapsulated in C star, or if it's freshly random, right? And clearly, if a scheme fulfills this notion, if those two cases are indistinguishable, then this means when I'm using an identity-based chem, I can just replace the key that's actually encapsulated there, right? In the case B equals 0, the C star information theoretically determines K. Or K star. Information theoretically determines K star in the sense that if my adversary was unbounded, he can just brute force a user secret key or a master secret key and generate a user secret key, right? And then decrypt the C star into K star. That's a case B equals 0. Whereas if B equals 1, then there's no relation, no correlation between K star and C star, right? That means in that case, my key K star is fresh and uniform, fresh and independent of everything else, right? It means once I've done a game switch with the security notion, right? What it allows me later in a bigger security experiment is to take the key K that's used in the real scheme and replace it with a fresh and uniformly random chosen key, right? Which is independent of the C star. And now I can use the security of whatever scheme I'm using with this key, right? Because it doesn't depend on C star anymore. That's an IB chem, and of course, the advantage is defined pretty much in the same way, right? So the goal of the adversary is to guess the bit B, and we say an IB chem is int IB chem secure if every PPT adversary A has only negligible advantage over 1/2 to guess this bit B. Good. Now here, I could say, show that I'm going to put this on an exercise sheet. IB chem implies IBE. All right, so give me an IB chem that implies IBE, and the recipe is clear, right? Recipe. No, there's no E in R. Recipe. We use IB chem plus symmetric key encryption. Hybrid encryption. This is good. All right. So why did I introduce this notion of IB chem? Because now we're going to talk about the famous Bonnet-Franklin encryption scheme. And in this scheme, which was originally written as or introduced as an IBE scheme, right? This is more naturally understood as an IB Chem in retrospect, because as an IB Chem, this encryption scheme, or this scheme of Bonnet and Franklin, has a few extra properties which we don't know how to achieve, a few bonus features, so to speak, right? Which we don't know how to achieve from many other identity-based or constructions of identity-based encryption schemes. Good. And I hope it doesn't surprise you that the magic sauce that will give us this IBE of Bonnet and Franklin is pairings, right? So that we're not, I mean, going all the way back, and it turns out identity-based encryption is something super trivial. No, it turns out that the key invention that led to, or the key innovation, so to speak, that led to this invention of the Bonnet-Franklin encryption scheme was Joule's tripartite key exchange, right? This is what spawned this, let's say, revolution in cryptography in the early 2000s. In 2001, it was first Joule and then Bonnet-Franklin that triggered this massive revolution with hundreds, maybe thousands of papers. And this, some of this stuff is actually now used in practice, specifically since blockchains became a thing, right? Since cryptocurrencies became a thing, this type of cryptography that gives us a much more fine-grained delegation of access. This is exactly what IBE does, right? It allows you to delegate decryption rights to identities, right? This is a sort of a fine-grained access structure, right? A cryptography with fine-grained access structure. This existed since the early 2000s, but somehow really only became interesting with the rise of blockchains and cryptocurrencies. And the idea of Bonnet and Franklin is kind of really simple, right? Last time when I explained Joule's tripartite key exchange, I said that, well, okay, let's do that on this slide. We're having Alice here, Bob here, and Charlie there, right? Charlie sends G to the C to those two. And then we can kind of think as Alice and Bob in this scheme, forming a virtual party AB. Right. This third virtual party, in a sense, interacts now with our friend Charlie, right? And what it sends back is, well, E, G, G to the A, B, right? So A has G to the A, B has G to the B, and from this we can kind of just publicly compute this EGG to the AB. Good. And now the question is, of course, when we think about here I'm saying, and a virtual third party, right? Will go into this. So here, I think when I write this here, the virtual third party, so to speak, is Bob. But I would say let's first look into the scheme, neatly fits onto a single slide, and then sort of assign or identify the roles of these parties. So of course, we're starting with a bilinear group of prime order T. And what we additionally need is a hash function, H, which maps from the identity space, right, binary strings of arbitrary length into the group G, into the source group G. And this is not important for the description of the scheme, but will later be important for proving security of this scheme. We will model this hash function H as a random oracle, right? So this is, for the security proof, collision resistance will not be enough for this hash function. We will need a little bit more. Okay, so what does the setup algorithm do? It just chooses a uniformly random X from ZP, sets the master secret key to be X and the master public key to be G to the X. Pretty simple, right? Just like El Gamal, only that we're now in a pairing group. Good. Clearly, we cannot use DDH or whatnot. But now comes the interesting part, namely the key generation algorithm. So the key generation algorithm takes the master secret key and an identity and now does the following. Takes the identity, hashes the identity, and raises it to the power of X. Okay, so we're not having G to the X here. This would be the master public key, but no, here we're having H it to the X. Okay, so it's basically something to the X with a different basis than G. All right, and now the final thing. Here, as I said, we write this as an identity-based chem. When we encrypt, we just choose R uniformly at random and output the ciphertext C, which is just G to the R, right? And our key, the key that the C encapsulates is just E of H of it, right? The encryptor hashes the identity, pairs it up with the master public key, and raises it to the R. Clearly, for this, we don't need an identity secret key or even a master secret key. Right? We just need the identity. So the hash function, this is important, is we think of this as public, right? Doesn't have to be part of the description of the scheme, or if it is part of the description of the scheme or the key, then included into an augmented master public key, right? We can always augment the master public key and put more information there. But here, this pairing operation is computed between H of it and MPK, and we raise it. Here, there's a typeset error to the R. And how do we decapsulate? So same error here. This is SK underscore it. SK it. Good. So the decapsulation algorithm also does something very simple. Just take SK it and pair it up with C. And the first thing, of course, that we have to look into is correctness, right? What does on the encryptor or encapsulator side, what's happening? We have E, H of id, comma, MPK, and raise it to the R. Yes? Yes?
Then again, how the encapsulation works, because I'm a little confused with the G to the R.
Mm-hmm.
The idea of the encapsulation is that it just takes a random element.
Yes. It takes the encapsulation algorithm chooses a uniformly random group element. That's my ciphertext, my encapsulation. but I need this witness R, this exponent R, that I've used to generate this random group element C to derive a corresponding key. Right? So the ciphertext, or encapsulation, as we say here, is just a single group element. Good. Again, this, you can think of an encryption scheme which encrypts random messages, right? You cannot choose this random message. The encryption algorithm chooses this random message for you, right? And then, of course, this random message, well, what do we do with random messages? They're good keys, right? If it's uniformly random or computationally indistinguishable from uniform, then we can use it as a key. Let's first look into correctness, right? So let's write things out. No, this is the same as E of still H of it, comma, and MPK is just G to the X. We raise it to the R, right? And now let's use linearity or bilinearity. Here we have H of it, comma, G to the X times R. Now, what I'm doing is I'm going to take the X and again use bilinearity, put it back inside, however, now on the other side, right? And what I'm going to do with R is almost the same. I'm going to take the R and I'm going to put it here in the second argument, right? You can also do that using bilinearity. So this is, oops, I wanted blue, E of H of it, H of it to the X, comma, G to the R, but H of it to the X, that's just my SK it. That's my identity secret key, right? That. So this is the same as E of SK it, and G to the R, that's just my ciphertext C. C, so this is the same as K prime, the decapsulated key. Okay? So we get correctness here. Great. Okay. And now let me see. We still got, before we go into the security proof, we still have some space. And the idea is again to study a little bit closer this connection with Jou's key exchange, right? Because when we compare this to Jou's key exchange, right, we could see things from the, let's say, when we encrypt, we could see this from the perspective of Charlie, right? The encryptor here has G to the R, right? And G to the R, he's actually including into the ciphertext. But then, what is he pairing up? On the one hand side, we have MPK here, which we know is G to the X. But now we have it's being paired up with H of id. And H of id, well, let's maybe also just write it in terms of the group generator, namely, let's write this as G to the Z, right? Now, basically this hash of the identity, this H of id, gives us the public key, so to speak, or the key exchange message of a virtual party, right? This this Z is in the real world chosen by no one, because we have this hash function. It takes an identity and just outputs a group element, right? So compute in the real world, computing this discrete logarithm Z corresponding to age of it is hard, right? This is a hard thing to do, and at this point, you're going to realize why we will use the random oracle model, right? So in order to have a security proof that reduces to the same hardness assumption as Zhu does, to the BDH assumption, we will need that age of it corresponds to some G to the Z. Good. And in a way, this knowledge of Z will enable the, let's say, knowledge of Z for non-challenge identities. It will enable a simulation of the of decapsulation of the DEC oracle. Simulation of DEC oracle, right? Because if we look at these things taken together, our basically what the decryptor does. The decryptor on this side here, he just takes, well, the decryptor will never be used, right? But he takes this age of it to the X and pairs it up with G to the R. This is how he finds his key K prime, and the encryptor here just takes pairing of H of it, right? And pairs it up with G to the X, or let's write it as MPK, PK, and raises it to the R, right? We've just seen those two things are the same, but now in the simulation, if you know what Z is, right, then you can kind of, now we're having this virtual third party. It doesn't exist in the real world, right? In the real world, no one knows what the Z is. But now in the security proof, right, we will model H as a random oracle, and that means the security reduction will know what, can choose this Z itself, right? It will choose the Z itself, and then we can sort of compute the key K in a third way, right? Namely, we're going to take MPK and actually, we're not computing keys here. So when we know this, H of, when we know this Z, then we're gonna simulate SKID as MPK to the Z, right? What is that? That is now just gonna be our, well, G to the X to the Z, which is the same as G to the Z to the X, which is H of id to the X, right? As required. But okay, that's just looking at this from the perspective of tripartite key exchange, right? That this message H of id could potentially be of the form, right, or corresponds to some z, which is just a discrete logarithm of h of id, or which could be seen as an auxiliary secret, right, that the security reduction will use, but that doesn't show up in the real world, right? In order, I'm trying, this is really a meta aspect that I'm trying to convey in this course. So in order to prove security, typically, right, we need to build a way for security reductions to kind of cheat the adversary. Whenever the adversary wants to, or when the security definition is such that the adversary kind of gets seemingly very powerful information, we need to be able to provide this information to him, identity secret keys, while making it such that this information isn't really of a lot of use to him. Right? We've seen that with the Kramer-Shoup encryption scheme before. Right? There, we could give the adversary a decryption oracle. Here, we're going a step further and even giving him identity secret keys. But just by setting up things carefully, we can make it that this additional information that the adversary gets is pretty useless, because sort of just by, in this case, simulating the random oracle, we can sort of cook up our own identity secret keys. Okay, but now we're going into the proof, which said, or into the theorem. The theorem that establishes security for this scheme, which says that BDH assumption holds in G, GT, E, and H is modeled as a random oracle. This is really important, right? For this scheme, we don't have a proof in the standard model when H is replaced, let's say, by a collision-resistant hash function. Not known. Then the IBChem that I just showed you, setup, keygen, and deck, is int IBChem secure. Good. So let's go into this, right? All right. Let A be a PPT. Adversary which breaks int IBChem sec of the scheme with non-negligible advantage epsilon. Good. What are we gonna do with this adversary? Well, we have to somehow turn him. Let's maybe write our adversary A here. We're gonna have to build an adversary B, which somehow uses this adversary A, right? But B has to solve BDH, right? So our adversary B gets a BDH challenge, which consists of G to the A, G to the B, G to the Z, let's call it G to the C. You know what? Let's already change the names of these variables here. Then I don't have to do a lot of renaming. So my BDH challenge here will be G to the X, G to the R, and G to the Z, comma E, G, and the third element, the Fifth element, let's just call it, what's happening? U. I want to call it U, or want to, you know what, let me use an uppercase letter for this. I don't want to call it U. I just want to call it, let's call it capital K, right? Where either K equals E G G to the XRZ or K uniform in GT. Good. So, and of course, this scheme is in the random oracle model, right? This is where our reduction B kind of gets its superpower because it can now simulate this random oracle H for the adversary, right? It's not that reduction B gets a random oracle somewhere from the outside and then just forwards access to this random oracle to the adversary. No, it simulates this random oracle in its own pocket. That's the, let's say, the advantage that my reduction B now has. Okay, so how do we go about this? Well, let's just cook up such a reduction B, right? Which is given our G to the, what to say, we start with G to the X, G to the R, comma, G to the Z. And, and this K, you know what, let's call it K star. Let's not call it K, let's call it K star. What is B gonna do? Well, it simulate IB chem experiment, but I'm gonna make a few changes. Yes, question? So where's the IB chem experiment? Here, this. Exactly the same, but we're going to make a few modifications to this experiment, right? The first one is going to be when it comes to the master public key, right? So instead of running the setup algorithm, we're going to do the following. Oops. Yeah. Set MPK equal G to the X, right? This is this element that it was, let's, you know what, let's use all in the same color here to make it a bit more, oh no, G to the X. This is just this G to the X, okay? That it gets from its input. So it gets G to the X from its input, and it sets that to be the master public key. Oops. Good. Okay, what's the next thing? The next thing is we have to simulate the random oracle H, right? The adversary gets access to this random oracle H. Simulate H. You know what? Let's make to make this a little bit simpler. Let's say assume A makes at most Q queries to H. Okay, so A is a PPT adversary, so it has sort of a fixed polynomial runtime, right? Its runtime is a polynomial, and we can just say, okay, if an adversary runs in time t, then it can make at most t queries to this random oracle, right? So if you're being given t steps of computation, then you cannot make more than t queries to this oracle, because I mean every query to this oracle is has to count as a computation step. But now we're just saying, look, let's say we know about Q, an upper bound Q on the number of oracle queries that our adversary makes. Good. So before we start simulating the random oracle, it just says choose I star from, let's say, 1 to Q, but not G, Q, uniformly random. Okay. And when we now simulate the simulation of H, so the way we simulate this H will just be the, let's say, the standard lazy simulation of random oracles, right? In the sense that every time the adversary queries the random oracle, we look if the adversary made this query already, right? If he did, then we take a stored value, and we've stored this value somewhere and just give him the same value again. If he hasn't queried the random, if he hasn't queried the oracle on this value, then, well, we choose a fresh output, store this output associated with the input, and give him this output, right? And let's maybe now say, assume for simplicity, right, that the adversary never asks the same query twice, right? Because again, I just told you how we could handle this. If he was querying the same query twice, we could just store all of the random oracle outputs and give those back to him, right? So on it, I here assume without loss of generality that A asks no query it I twice. Good. Let's say what we do here is keep counter I for the number of queries A has asked so far. Right? So in the beginning, this counter is initialized with 0. Then he asks the query. All right, gets an output. Then we're incrementing this counter and so forth. And we know this counter can never exceed Q. Good. But what are we now doing? For I not equal I star, choose uniformly random, choose uniformly random ZI and output and out what's happening, output G to the Z, G to the ZI. ZI. But for I equals I star, output, now we're using a different color again, not red, but let's use orange. We're going to use this guy here, G to the Z, okay? So what the reduction does is it guesses an index of an Oracle query ahead of time and speculates that for this query, you will use this query sort of for its challenge identity, right? And that's where we're gonna put part of our, that's where the reduction will put this G to the Z from its own challenge, right? The reduction just hopes that the adversary chooses this value it I star, this identity it I star as its challenge identity, right? Good. So how are we proceeding here? Now simulation of keygen. So keygen gets the keygen oracle gets as input some identity it, and first thing is if it is the same as it I star, right? Abort and output bot. So again, the reduction guesses this index it I star, and maybe the adversary has already queried this it I star, right? If so, all right, then there's nothing we can do. Then we have to abort the simulation, right? Because if the adversary in the first phase queries the keygen oracle on this it I star, then it I star cannot be the challenge identity anymore. Then the adversary cannot use I star as or it I star as its challenge identity it star, and the reduction guessed wrongly and has to abort. Otherwise, set otherwise output skid, which is just MP otherwise, let's do it a little bit more in detail. Find I such that find I such that id equals id I, right? From the adversary's random oracle queries. If A hasn't queried age on id, query H on id on behalf of A, right? Why can we do this? Why can we let the reduction query the random oracle on behalf of the adversary? Well, again, we said we have an upper bound on the adversary's oracle queries. There we can just include the keygen queries, right? We can just say, when we count the adversary's oracle queries, let's just also include all the keygen queries. Let's be generous, right? Let's overcount slightly. That's not going to be a problem. And again, just by this small simplification, we're just making writing this proof easier without really omitting any actual details. Okay, just by saying the simplification, if the adversary hasn't queried this the random oracle on this identity, we are going to make this query on his behalf. Okay. So what's the time? We still have 10 minutes. I think we might not be able to finish this. But then output G, sorry, not G in this case, output MPK to the ZI, right? Which is, of course, the same as G to the X to the ZI ZI, and which is, of course, H of id to the X, right? We don't, of course, we don't know what X is, right? But now we've simulated H of id to the X for the adversary, right? Even though we don't know what X is, just by virtue of knowing what the ZI term is, just by virtue of knowing a discrete log of this hash value. Okay, that's the oh no, oh Jesus, I need to add a few more slides here. I've seen how did I think this proof would fit on 3 slides actually at page. And now it's adding a big page. Anyway, good. Let's leave it at this. Good. And finally, yes, question?
Yes, about this part that so if A hasn't queried the H before.
Yes, the it. Sorry. H on it before, yeah.
And the random oracle does this for A. Yeah.
So the reduction queries the random oracle, right? I mean, we're now already at the simulation of keygen, right? So we were up here, we were at the simulation, let's say here, we were at the simulation of H, right? The random oracle, and here we're at the simulation of keygen.
Oh, okay.
Good. Okay, so now we're almost there, right? I said simulate the IB Chem experiment, but I made quite a few modifications. So first modification was I'm setting the master public key to G to the X. I'm choosing this index I star. I'm having a rule to simulate the random oracle, and I'm having a rule to simulate keygen. Now, the last thing I'm gonna have to do is good. The following rule: how I generate the challenge ciphertext. Generation of challenge ciphertext. Good. If A hasn't queried if A hasn't queried H on its star, query it on his behalf again. Right? So if the adversary hasn't queried the random oracle on the challenge identity, then we are going to do it for him. Good. And now this is really for simplification, which whenever I write, if A hasn't done this, then we do it for him. Then this just means actually a smart adversary would do this by himself. He has all the capacity to do that. So please, if he hasn't done it, well, then we do it for him. But now we're going to do the following. If id star is different from id I star, right? Remember, we've guessed in the beginning this index I star. And now if the challenge identity is not id I star, abort and output, let's say, up here I said output bot. 1 second, and output random, let's say random bits. Random bits. That makes the analysis slightly easier. But we could as well. Bit, right? Otherwise, the wise set C star to, well, there we have this. Now let's use a different color again. What color am I going to use now? Maybe this green here. G to the R, right? The stuff that we were given here. And now let's also use a different color for K star. But I think we're pretty much just purple. And run second phase. Second phase of A on C star, comma, K star. Right? The rest of the experiment is the same. Okay? Good. But to do the analysis, to analyze these two cases that we essentially have, right? 3 minutes will not be enough. So I think let's do that next week. I think we still have one lecture before the vacations. Correct me if I'm wrong. So the 23rd. So are there already vacations on the 23rd? There are? Okay, good then. Okay, good. Then I slightly misplanned here. Then yeah, then what's left at this point already is for me to wish all of you happy vacations and a happy new year, and I hope to see you back in the same spirit in the next year. Thank you.